Matched pair design. So we'll get to an actual calculation of that at the final exam. But for now, just know what matched pairs are. So sometimes they match up identical twins, sometimes husbands and wives, like income. But most of the time, it's the same people tested before and after something. Or it could be like they test your right arm with one type of insect repellent, they test your left arm with the other. It could be testing blood pressure before and during tax season of accountants. Could be giving some students a discovery lesson in math and measuring their math scores on a test before and after it. Statistically significant means that the observed effect is so large that it's unlikely to be just due to chance. So usually there's a question on the different types of ways to sample. So voluntary response is just what it sounds like. People volunteer, so they're not selected by the researcher. They call in or write in to a radio station, things like that. They tend to have strong views. So it's not the best way to get a sample, obviously. Convenience, same thing. It's not going to be random. Convenience is ask people convenient to you. So friends, people in the same lab section, something convenient. Simple random sample is each individual has the same probability of being chosen. So everyone has the same chance. So something like random number generators, or put all the names in a hat, mix them all up, pull one out, something like that. Stratify, divide the population into non-overlapping groups. Non-overlapping groups called strata. And then the key is you choose a simple random sample of each group or each strata. So that's different than cluster. People mix them up. In cluster, the top of the next page, we would randomly select a couple groups and ask everyone in those groups. Whereas in stratified, we divide the population into groups and choose a simple random sample of each group, okay, of each group. Cluster, we divide them into clusters or groups. And then here is the key, randomly select a few clusters and perform a census. So ask everyone in the randomly selected groups. And systematic, at the bottom of the page is, you stand at the library door and ask every 10th person who comes through the door. So every kth individual. Okay, so non-probability or non-random sampling methods. So we talked about convenience. So there's a few more, judgment, quota, and snowball. So judgment is a non-probability or non-random sampling method. The researcher selects the sample based on their own judgment. So I know one time in a different stats exam, they said the person who's performing the experiment decided to pick people based on who they think looked intelligent in the group. So that was just based on their own personal judgment, okay? Quota sampling is when you need a certain percentage. You have to fulfill a certain quota. So there's an example down here, like if you wanted to set a quota of 3% of the Muslim population to be in your sample, then you would make sure that you got that quota to guarantee that the views of the Muslim population was represented in your survey. Snowball sampling is when the characteristic that you want to find out about is extremely rare. So it's hard to find different subjects. So it relies on referrals from initial subjects to generate additional subjects. So you find this person and then they give you this person's name and then they give you this person's name. And it just kind of snowballs like that. Okay, so non-response is people who cannot be contacted or refused to answer. Response is people are biased, people can lie in their responses. Undercoverage occurs when part of the population are left out. So for example, the homeless might be left out in terms of your survey. Confounding, variables are confounded when the effects on the response variable cannot be distinguished from one another. So the variables are confounded if we can't say that this caused this because there's other variables going on. So if we go back to the vitamin and measuring colds, you have to control all of the other variables so that there's no confounding of variables. So things like exercise, healthy eating, what other vitamins are they taking, what other medications, things like that would all have to be established and controlled. Okay, so lurking variable is a variable that's not among the explanatory response variables, but may influence the relationship or what the cause and effect is that you're stating. So a variable is confounded basically when there's a lurking variable. So they're the same, basically the same kind of thing. Okay, a lurking variable might be something that affects your data, but isn't one of the variables that you're studying. Okay, we talked about independent, we talked about factor, treatments, treatment levels, so you can kind of see that from here. If you've got 3 different levels of vitamin C and 2 different levels of vitamin E, then you've got 3 times 2 is 6 different treatments. Okay, we talked about block designs, I think that's it. We talked about matched pairs. So look at the bottom of page 67 here. Okay, a study about sports preferences of Western students involved a random sample of 100 students. Rachel surveyed 40 first-year students, 30 second year, 20 third year, and 10 other students. What type of sampling is this? Okay, so write down what you think. So we're taking a random sample of each group, first year, second year, third year, other. So that's stratified, taking a random sample of each group. Nicole stood outside No Frills and asked every 10th customer to fill out her survey. Okay, what's that called? So that's called systematic. Oh, that one, sorry, I'm on the wrong question. What type of sampling involves the population divided into non-overlapping groups so that each group is represented in the entire population? So each group is representative of the entire population. That's cluster. Okay, now there's one little bit of math in this section, and that is random digits. So if we have like a list of, in this case, restaurants, but it could be people or whatever, we number them. So if there's only, 10, we can let them be 0 to 9. If there's like 300 of them, then we'd have to go 001, 002, all the way up to 300. Okay. If there's only 50, then we can do 2 digits. So it depends on how many total there are on how many digits you use. So this one has Wendy's all the way to Taco Bell being 0 to 9. And we've got this random list of numbers. So we have to go through the list from left to right and take the first 4 numbers. We want to, it says up here, we want to call 4 of the restaurants. So we're going to take the first 4 numbers. And we only circle 1 at a time because everybody is represented by 1 number. As soon as everyone has to be 2 digits, then you'd have to circle 2 at a time. So the first number I'd take would be Archie's. And then number 9 would be Taco Bell. 0 would be Wendy's. And 4 would be Jack Astor's. So I would take those restaurants. And it doesn't matter what order you list them in, as long as you have the right 4 restaurants. So sometimes they'll mix up the order of the numbers and not give them in the order that you got them. And that's okay, as long as it's the same 4 numbers that you got. Okay, so as soon as there's more than 10, then we need to use 2 digits to label them. So everybody's 01 up to 13. So this can't just be the number 1 anymore. Okay, everyone has to be the same number of digits. Okay, so I'm just going to make this a little bigger for a minute just so that I can circle the numbers a little easier. Okay, so we have to circle 2 digits at a time, and we're looking for anyone between 01 and 13. 01 and 13. And we'll take 4 again. So 69 is too big because it's not between 01 and 13. But 04 is okay. That's definitely between 01 and 13. 38 is too big. 12 is good. 35 is too big. 90 is too big. 72 is too big. 13 is good. Notice I'm not skipping any numbers anywhere. And 01 is good. So those would be the 4 that we would use. So 04, 12, 13, and 01. There is no 07. So you have to circle 2 at a time. So there is no number 07 because it's 90 and then 72. So you can't just circle like all over the place. You have to circle 2 at a time in order. Okay, and those are the numbers that you get. So there is no 07. It's 90, 72, 13. Okay. Alicia is testing a new medication. She's going to give the new medication to subjects suffering from depression, and after a month, see if their symptoms are lessened. There are 16 subjects available, numbers 1 to 16. So we're going to go 01, 02 up to 16. It doesn't matter what these numbers are going up by. It matters that every one of these numbers, these places, is being represented by 2 numbers. So you circle 2 numbers at a time. You don't leave any numbers out. 2 numbers in order. Don't leave any numbers out. Okay, it doesn't matter what numbers go up by. It has nothing to do with that. It has to do with the fact that everybody is represented by 2 digits. So you circle 2 at a time without skipping any numbers. Okay, so for this one, we have to circle 2 numbers at a time. Everyone is 2 digits. Again, don't leave any numbers out. And it says that 4 of the subjects are to be given the new medication and 4 to be given the placebo. Find the first 4 subjects to receive the medication. So if it said find the second 4, then you'd have to find the first 4 and then keep going and find the second 4. But this says find the first 4 to receive the new medication. So I'm going to make it bigger again so that you can see the numbers better. So here, we circled 2 at a time. Everybody has 2 digits, so we're circling 2 at a time without leaving anything out. So 81 is too big. 05 is the next number, and that is okay. That's between 01 and 16. Don't leave any numbers out. So 72, too big. 71, too big. 02 we can use. 56, too big. 0, 2, we can't use the same person twice, right? We have to pick 4 people, so we keep going. 75, too big. 58, too big. 92, too big. 33, too big. 0, 6. 34, too big. 18, still bigger than 16, too big. 42, too big. 81, too big. 86, too big. 87, too big. And 10. So those would be the 4 we would take. Okay. All right, flip to the next section. Okay, sampling distribution starts on page 76. You'll never run out of numbers. You'll always get it by the time you get to the end of the list. Yeah. Okay, so we talked about parameter refers to a population. Mu and sigma are parameters. So mu is the population mean, sigma is the population standard deviation. Statistic refers to a sample, so we have X bar and S. So here we talk about the law of large numbers. X bar is rarely exactly right, varies from sample to sample. If we keep taking larger and larger samples, X bar will get closer and closer to the mean. So the mean of the sampling distribution approaches the mean of the population. The standard deviation of the sampling distribution approaches sigma over root n. Okay, so those you have to memorize. So our formula for Z versus the old formula, Z was X minus mu over sigma. Now it's X bar minus mu all over sigma over root n. This question here is going to ask about the mean or the average or sometimes the total to try and trick you. So mean, average, or total. And so that's how you know it's not just a Z equals X minus mu over sigma. Now the central limit theorem says that if n is 30 or larger, you can use the normal calculation, the Z formula, even if it doesn't say normally distributed. Okay, so that's the sort of the magic number. On one of the old exams, they used 40. I'm not sure why, but you guys, can you just type in the Q&A, use 30 this year, right? I just want to make sure both classes use 30. Anybody type in to make sure that you use 30 this year? Okay, good. All right, just making sure they didn't change anything from one note to another. Okay, so n greater than or equal to 30. So here's the key. The central limit theorem allows us to use the normal probability calculations to answer questions, even when the population distribution is not normal. If the distribution is not normal and n is less than 30, then you cannot use the Z. And then you might have that kind of answer that's not enough information to calculate, sort of a thing. Okay. So number 1, a meat packaging company provides packages of sausages to customers. The weight of the sausages are normally distributed with a mean of 3.5 and a standard deviation of 1.06. If the meat packaging company gets an order for 20 packs of sausages, what is the probability the order will be less than 75 kilograms? Okay, so the order will be less than 75. So they're giving you a total there. So normally distributed, so we know it's Z. Standard deviation, 1.06. Mean, 3.5. And it says the order will be less than 75. So that's the total of 20 packages. So let's get the mean example. If we have 75 kilograms divided by 20 packs, that's a mean of 3.75. So we have the probability X bar less than 3.75. They want less than 75, so that would be less than 3.75. So do your Z formula, X bar minus mu all over sigma over root n. So we have 3.75 minus the mean, which is 3.5, all over sigma, which is 1.06, over root 20. All right, so type in one of these just to make sure you don't do anything silly so you can catch it. So you can either do this minus this equals divided by 1.06 equals times root 20 because it's divided by a fraction, or you can put the bottom in brackets. You should get 1.05. So we wanted X bar less than 3.75, so that's Z less than 1.05. So get your table out. 1.05.8531 is below 1.05. Okay, any questions about the first one there? Okay, the weight of corn chips dispensed into a 10-ounce bag by a machine possesses a normal distribution, okay, with a mean 10.5 and a standard deviation 0.2. Suppose 100 bags of chips are randomly selected. So that's our N. Find the probability that the mean weight exceeds 10.45 ounces. Okay, so the mean weight exceeds 10.45 ounces. So we know this is the special formula that has the X bar in it because it says mean. So it has to be X bar. So we want probability mean greater than 10.45. So sub it into your formula and see what you get here. We're on page 78. Okay, so we have X bar 10.45 minus 10.5 all over sigma over root n. So we have Z equals negative 2.5. So draw it out. So look up the area below negative 2.5, and then you can subtract from 1 to find the area that you want. So area below negative 2.5 is 0.0062. So that's in here. So the area we want is 1 minus that, or 0.9938. Okay, any questions? Okay, so then we have this finite correction factor. If you're given the population size, then you need to look for this. So look for questions. 10.45 was given in the question. Question says mean weight exceeds 10.45 ounces. So right in the question. So look for questions where the size of the population, big N, is given. If big N is given, you're going to check little n over big N and see if it's greater than 0.05. If it is, then you have to add in this root big N minus little n over n minus 1, all under a root. And that'll get added into your answer. Now, there's not very many questions on an exam where they give you the population. It's very rare, right? So look for this, and if you see it, then look for n over n and check it. And if it is greater than 0.05, then add this portion in. One of my students in my tutoring got a question on one of their question sets where they had a confidence interval and they made them add this into it because they had the population size. So watch for that as well when you get to confidence intervals. Okay, so suppose a normal population of size n equals 800, so big N equals 800, has a mean of 85 and a standard deviation of 9. Random sample of 81, so that's our n. Find the probability that the mean is less than 88. So mean less than 88. So we'll check n over n. So we have 81 over 800, which is about 0.1. So that's going to be greater than 0.05. So therefore, we use the correction. So let's work out sigma over root n, and let's work out root n minus n over n minus 1. So sigma is 9 over root 81. That's 9 over 9 is 1. And here, n minus n, so 800 minus little n, 81, over 800 minus 1. And if you type this in and you keep all the decimals, it's 9486173332. I like to do these off to the side and then put them in. I find it easier than trying to type in the whole thing all at once because it gets to be a bit crazy. So the whole formula is there. So we have x bar is 88 minus mu, which is 85, all over. This was 1, and then that decimal. And so if you do the rough work off to the side, it just makes it a little easier with typing in this Z answer here. So this works out to 3.16. So we had X bar less than 88. So now what do we do? Write down what you think you're going to do next. So we have X bar less than 88 means we have Z less than 3.16. So look up the area below 3.16. So 3.1, 0, 1, 2, 3, 4, 5, 6. 0.9992. And that's our area. Okay, so that's chapter 7. Now we're going to start chapter 8, and then when we work on hypothesis testing, we'll work on confidence intervals and hypothesis testing at the same time. So it'll be chapter 8 and 9 sort of mixed together, just because the questions are all going to be mixed together on the exam anyway, so that's how I do it. Any questions about anything in here for chapter 7? Okay, so flip to page 85. Okay, so we're going to talk about confidence intervals first for Z. So if we have, let's say, a 95% confidence interval, then we are 95% confident that the true population mean is in our confidence interval. So let's make up a confidence interval that goes from 10 to 50. Then we are 95% confident that the true population mean is between 10 and 50. The width of this interval is 50 minus 10, which is 40. The margin of error, which you call E, is half of the width. So it would be 40 over 2, which would be 20. Now, there's critical numbers that probably a lot of these you'll end up memorizing by the time you get to the test because you use these numbers a lot. So for 90%, it's 1.645 is your critical Z. 95% is 1.96. 98% is 2.326 or 2.33 if you round it. And 99% is 2.576. So those are the critical numbers that we'll use for confidence intervals. And you can call the critical value Z alpha over 2 or Z star. Okay, so you can look these up on the bottom of your T-table as well. So if you have your T-table handy, great. If you don't, you can look in the back of the book. It's on page 203. Have all your tables ready for tomorrow if you didn't have them ready for today, just so that it saves you time from flipping back and forth. So in terms of your T-table, 90% means 0.05 in each tail. 0.05 in each tail means 10% total in the tail, so 90% in the middle. 95% is the next one, 2.5% in each tail, or a total of 5% in the tails. And then this one is 98%, and this one is 99%. So if we follow these let's say we look at the 90%, if we follow the 90% all the way down to the bottom, where it says infinity, that's the Z, or the Z alpha over 2. So that number at the very bottom of the t-chart, so as the t-chart approaches infinity, we get to the Z table numbers. And so that's 1.645. That's a 90% confidence interval. That's the critical number. This one, 95%, 98%, 99%. Now, of course, you have to know when they give you like 92%, then you can't just look it up on the t-table. So I'll have to show you how to draw that out and calculate it using the Z, the table like that we've been using for Z. Okay, so some words to know that you're using Z. So using Z. So number one, if you know sigma, the population standard deviation. Number two, they might say process standard deviation. That means population. They might say from past records. That also means that you're using sigma. And they might say nationally known. And the last one that I've seen is manufacturer specifications. So these all mean you have sigma, and so you use Z. So the confidence interval formula is at the top of the page. I'll move this up as soon as you guys are done writing it. So confidence interval here, x bar plus or minus critical Z times sigma over root n. Sigma over root n is called the standard error. The margin of error is the whole thing, the Z alpha over 2 times sigma over root n. So that's margin of error. Okay, and the standard error is just the sigma over root n. So if he asks you to find standard error, you don't put the critical Z in. If he asks you to find the margin of error, then you do put the critical Z in. Okay. So in terms of the formula, so we know the margin of error is critical Z times sigma over root n. So few observations. As sigma increases, E increases. As the critical Z increases, E increases. Okay, and that's because the critical Z and sigma are both on the top. But as N increases, N is on the bottom, so that's going to make the margin of error go down. So they're inversely related, N and E, whereas these are directly related, sigma and E and Z alpha over 2 and E. So Z alpha over 2 gets bigger, E gets bigger. That means a 99% confidence interval is wider than a 90%. Has to be wider because you're more confident that you got the mean in there, right? So it has to be wider because you're more confident you've encompassed the mean in there. So as N increases, E goes down. And it's not just a linear relationship, because as N increases by 9 times, E goes down by root 9 or 3 times. Okay, because of that root N. Okay. So if you're testing the mean is 12, the mean is not 12, and you have a confidence interval here, then you check, is 12 in your interval? That's how you make your conclusion. And in this case, 12 is in here, right? So we would say, therefore, do not reject H naught. So yes. So therefore, we call it fail to reject H naught. We'll talk a lot about what that means when we get to hypothesis testing. But if we have mu equals 14, then it's not in there. And so that would be a reject H naught. And rejecting H naught would mean that we're assuming H naught is not true and that HA is true. So if you reject H naught, then you're assuming that it's false, and then the alternative is true. And if you don't reject H naught, then you're assuming that H naught is true and the alternative is false. And again, we'll go through that a lot when we get to hypothesis testing. Okay, so let's take your other break now before we get into examples of confidence intervals here. Okay, so take a break. It's 2:30, so come back at 2:45.